Okay, thank you.
Sorry about that.
So just to show you this doesn't just work for introductory physics. These kind of methods have been used in a whole variety. This is where the same teaching method and same comparison is done in the 4 kind of core introductory computer science courses. This is done at University of California at San Diego. And there it was the same instructors, but they simply switched from the traditional lecture method to these research-based teaching methods. And they looked at the failure rates in their courses. And you can see across all 4 courses, the failure rates here dropping substantially. And so this is an example of you have the same foreign teachers, but they simply changed their methods, with the result being now the failure rate is about 1/3 what it used to be. And so many more students are now able to successfully pursue a career in computer science simply because of the quality of teaching is better. Now, most of the research on this has been done at these large introductory courses, but my group and a few others has been applying the same principles in more advanced courses, and particularly across physics courses. And so most of the courses taught by or taken by Stanford physics majors are taught in this way. And it's even been shown to be highly effective for a very advanced graduate physics courses, as well as many other disciplines. But all of these courses have this same basic structure that research has shown is effective. The students have to do a little bit of preparation before class, and then during class, they'll be working through activities. In this more advanced physics classes, they're worksheets with complicated problems, but the students will be working in small groups while the instructors are monitoring how they're doing. And then periodically, every 10 or 15 minutes, then the instructor will pull the class together, provide feedback, answer questions, and sort of bring all the students up to a similar level. And then the students will continue going back and continue working through the activity for the duration of class time. And the key features in this are that students are thinking, they're practicing expert reasoning, and the instructor is much more knowledgeable about their thinking and so can provide them with more effective feedback. So we've got many studies like this from many disciplines, and so I won't go into all, too many, but they consistently show greater learning, and they show lower failure and dropout rates. And as I sort of talked about as I went along, we understand why this is happening, what happens actually in the brain to make this work. But now I'm going to turn to really getting very detailed about what detailed findings we have from the classroom research. And so these are things that if you're a teacher, you really can go and use immediately in your teaching. Now, the key, this is kind of a summary of all the very broad, many hundreds of studies on teaching science and engineering more effectively, and what factors matter. And the key, of course, is, as I said, the students are practicing making meaningful decisions, problem-solving decisions with good feedback that's timely and specific and action guides them how to improve. But there's a lot of things that matter in terms of really making this highly effective. Just like in any area of science, there's lots of important factors. And there's the ones up at the top really determine what goes into making good practice activities, and the ones down at the bottom go into how to implement these effectively in the university classroom setting. But this body of work really defines teaching expertise in a way that one couldn't have done 20 years ago, or even several years ago. But it identifies specifically what practices research consistently produce more learning, better outcomes in students. And so it really tells you these are the things you want to be looking at in a teacher to see how effective they are. Now, I'm going to go through just a few of these to give you some ideas of what's involved in this. Starting with the disciplinary expertise. They've got to be practicing making decisions, but these are the kinds of decisions that a person in that area of science needs to do to be a good problem solver. And this is something my own research group has been studying for the last several years, and we find that to solve problems effectively, which is what, that's what scientists and engineers do, it always involves making a set of decisions with limited information. And the thing that was surprising to us is as we studied this across about 50 scientists and engineers from a whole variety of disciplines, we found they made the same set of decisions, and it was not a tremendously large number. It was 29 sort of defined every step of their problem-solving process. And you might think it seems impossible they could be making the same decisions, but I think once you see what those decisions are, it makes more sense. There's when they start out with a problem that they're considering, they have to decide what concepts and mental models are relevant to solving that. They have to decide what information provided is relevant, what's irrelevant, and what information is needed to solve the problem. Decide what approximations or simplifications are appropriate, and then deciding on the potential solution methods that they should pursue. And then they go through a bunch of others. As they get new information through their solution process, they have to decide how credible that information is and what conclusions they can draw from it. And then once they get down to a solution, they have to decide, does this make sense? They have to decide how they can test it. So I think pretty much anyone who's in science and engineering looks at this and says, yeah, that's the kind of things I have to be doing in my work. But even though the decisions are the same across all these different disciplines, how to make those decisions for a particular problem, that always requires quite specialized disciplinary knowledge. And so this part is general across disciplines, but there doesn't mean that you can solve problems in another field, because you have to, really a test of a good problem solver is how effectively they realize what information can guide them to make these decisions and applying that information well. So this is just showing you kind of the general categories of decisions we've found. There's deciding on the importance of the problem and fit to the solver's expertise, deciding on the specific goals, framing the problem more specifically, and that goes into design potential solutions, etc. Planning how one will go about solving the problem, setting priorities, etc. And then collecting and interpreting information, and then from that working your way to actually testing and refining candidate solutions, and then finally deciding on the implications and communications. And so now, although I've sort of presented them as a nice logical order, in fact, what we see is that they aren't at all, that in the process of solving this kind of problem, the scientists will be jumping around back and forth, re-examining, starting over, skipping between different places. And so, and many of these decisions will be made many times during the solution process. Now, if you look at these kind of decisions and then ask, okay, how do I go and teach students to be good problem solvers? Well, as I told you, the brain learns what it practices. And so to have a student really learn these things effectively, it has to be practicing making these problem solving decisions, and it's got to be making them in realistic problem context. And so that's very different from the kind of usual school problem that students do, where they're given all the information they need and no other information. They're they're told what approximations to make, what things to assume, and so on. But that just removes all of the making decisions. Instead, it reduces problem solving to simply memorize procedures, which gives you no help for solving real problems. And if you think back to my original puzzle about how these incoming physics graduate students could do so well in courses and not know how to do physics, it was exactly this reason, that the courses weren't providing them with the practice they needed to actually learn to be good problem solvers. And so we see in our research and many others, we see this happening over and over again, that students learn information, they can do well on exams, but when they're called upon to actually how well they can apply that information to solve problems, they're no good at it because they never had that practice experience. So that's these kind of the disciplinary expertise in making decisions in the context of a discipline and using that information. That's this part. These two are kind of obvious to people, that the problem practice has to be matched to the level of the student's prior knowledge and experience. If it's too easy or too hard, it's a waste of time. And motivation is really critical, because what we know is that for the brain to learn, it's got to be working very hard. And so the student has to be motivated to put in that mental effort. But the brain constraints are something that cognitive psychologists know well, but are really badly neglected by most university teachers. And so I'll say a little more about that. And the important things is the memory. And so if you look at the way the human memory works, it actually has two parts to it. There's what technically is called the long-term memory, and that's what most of us think of as memory as being. It has this enormous capacity, and it can remember many things for years, decades, and so on. But it turns out there's another aspect to memory, and this is cognitive psychologists call this the short-term working memory. And it's really a buffer, that information has to go through this buffer before it can get into the long-term memory. Now, this working memory, it has a tiny capacity. It's about, for the typical human brain, it's about 6 new items, and it's got a time scale of minutes that it can remember things on. And it's really, you can think of it as, it's the amount of things and time that the brain can pay attention to. But now, this very small capacity is really important, because anytime, the brain hears or sees something new, that information goes into working memory, but because it has so much a small capacity, that means it always pushes something out. And that something that it's getting pushed out is not getting into long-term memory, not getting processed and learned. So in the context of teaching in a classroom, an hour or so long classroom, the constraints from this working memory are extremely important. And because what it means is that any additional thing the brain's paying attention to, it's reducing the attention and therefore learning of something else that's being presented there. And so one aspect of this is split attention, where if the students are, in a lecture theater, if their teacher's talking, but the student's also looking down at their mobile phone and texting, email, or anything like that, this is just a disaster for learning because it's using up most of their working memory capacity. And this is actually one of the things that's particularly bad about with the pandemic and virtual learning, because listening to a lecture is not very effective in real life, but it's even worse when it's on a computer and you've got all those other things on the computer screen that can get your attention and distract it. But there's also many things instructors do without realizing the damage it's causing learning. And it's things like using unfamiliar jargon, putting in some really fancy, colorful picture that gets attention, even though it's only some little piece that you care about illustrating. And it turns out even those funny little stories or jokes, they actually hurt learning, because all of these things require the brain to pay attention to. It uses up this working memory capacity, and therefore drives out the key things that you hope that people will be learning. And so the lesson is one just has to recognize this cost of any additional thing that the students are paying attention to, and really try and keep the focus only on the key items and issues and attention that you want them to learn. Now, there's another important aspect of memory that matters, and that has to do with the long-term memory. As I talked about, there's hard to get things into it, but it turns out it's not incredibly hard. The harder part about long-term memory is the recalling of the right material later on. And one aspect of this that's really not appreciated in teaching is that recalling things later on, the biggest problem is the new stuff that was learned afterwards. In other words, you've learned something and got it all figured out, but then you go and learn other material and neurons couple in there. And so the pathway from a problem to the information that helps solve it has a lot of interference with these additional neuron connections. And so what that means is that our typical teaching process of let's cover chapter 1 material and we have homework and exams on it, that's all learned. Now we can stop. We don't have to worry about that. Now we'll cover chapter 2, do it, then chapter 3. But in fact, if you go back and measure things carefully, you'll find that the process of covering chapter 2 and 3 really hurts the learning of chapter 1 and the recall of chapter 1, the correct recall of chapter 1 material. And so, but it turns out there's a way to solve this, which is that you just have to go in periodically as you're covering chapter 2, 3, and 4. You have to just periodically, occasionally spend a little bit of time going back and thinking more about chapter 1, and that cleans up all this growing interference, and so people can have much better recall of long-term recall of material if they have this kind of occasional re-examination of old material while they're learning new material. So let me say a little bit now about the research on the implementation of these teaching methods in the classroom. What I've talked about now is just what has to go into designing things the students should be practicing, but how they're handled in the classroom is also important. And one of the things that's probably the most important is it's not good enough to just say students work on this problem. It's important that there be quite clear and specific deliverables, things the student has to work through to complete, where they will, and I keep coming back to, they'll be making particular decisions required in the problem. For example, you know, with what information's needed to solve this problem, and justify why you've decided those are important. And so, and they have to write that down so the instructor can both see that they've done it and reward them for the effort, but also can see what they're doing and thinking and be more targeted, more useful in the feedback they provide them. So it's not enough, you know, you have to have clear deliverables. When you want the students to discuss with each other, there has to be clear goals to that discussion, what's supposed to come out of their discussions. Now, there's another aspect that research is shows it's a very effective tool for helping learning, and that's what I'll call social learning. And basically what we see is that students learn a lot more if they work in small groups. A good size is in class, a group of 3 or 4, like I showed in those pictures there, working through these problems. But there's I see again a very common question from instructors who say, well, I can see having students work on problems might be good, but then it makes much more sense for them to hear me as the expert instructor explain the answer to this rather than having talked to their fellow students. Now, it might seem that this is right, but that's not the way the brain works. In fact, the way the brain works says, and we have data, actually lots of data from my own group and many others, showing the process of talking to fellow students contributes in many situations, contributes more to learning than actually hearing an instructor, an expert explain it. And there's it's a really interesting brain aspect of this, actually, which is that the brain, it's clear that has sort of special circuitry, if you like. And so that when a person's called upon to teach something to someone else or explain it to someone else, or even prepared to teach something to someone else, it actually triggers a unique cognitive processing that goes in to how they think about that material. And this kind of special extra social cognitive processing contributes substantially to learning of the subject. And finally, it's also very useful when you're just as a side point to teachers, to hear those student conversations by having students work together, just because it gives you a better understanding of how they're thinking, and so how you can help and better guide that thinking. Now, some advice I give to students, you can help yourself learn new material on your own by doing sort of one simple exercise. Every time you're struggling with studying some new material, step back and think, okay, let's say I have a younger brother or sister. How could I explain this topic, this material to them? And just the process of thinking how you would explain it actually helps you understand it better. So I'll just finish up here and then we can take time for questions. I mean, we have research now that's quite extensive showing the best, how to achieve better learning at the university level, and both the students have to be practicing thinking with good problem design and good implementation in the classroom. But we have good data that if that's done right, it's much more effective for learning than the traditional lecture teaching, and we can really understand down to how the brain works as to why that's true. Now, before we start I start taking your questions, I'll ask a question of my own, or I'll repeat a question I hear many, many times when I give this talk, is that, especially when I'm telling university faculty members that they've been lecturing for years, it's not really very effective. They'll say, well, but look at us university professors. We were all taught by traditional lectures, and look at how, successfully we turned out. And my response to that is, if you look at bloodletting, it was the medical treatment of choice for 2,000 years. And it was based on exactly the same reasoning that, okay, people had bloodletting and they survived, so and became doctors, so it must be effective. But of course, we know that's not true, that just as in medicine, now what we've learned in good education research is you have to have a comparison group. So, university professors that were successful by hearing lectures, they likely would have been even more successful if they'd been taught by these more effective methods, but also more reasonably, many more of their fellow students would have become much more successful. So with that, I'll just end. I've covered a lot of things rapidly, so I'll make sure my slides will be available so that you can get them and look over them yourself. But also, here are some a set of good references that I have on learning more about the things I touched on here, the research behind it, and the ideas and insights that come out of it. So with that, I'll thank you for your attention and take questions.
Thanks, Prof. That was most illuminating. We would like to open now the floor now for questions, if there are any. But maybe, Prof, I would like to pose this to you. Is your approach similar to what we call as PBL, problem-based learning?
PBL, it has some elements of problem-based learning, but problem-based learning is sort of starting with a problem, and so that's incorporated into this, but it has many features that go into the detailed design of what that problem is and how it's actually, the students are actually working through it in the classroom. So I would say that problem-based learning is sort of a piece, but it has to have a bunch of other things around it to be properly optimized.
I see. So we have to have additional stuff for just instead of just problem-based learning.
Yeah, it has, or you could say it's a very complex, careful implementation of problem-based learning, I guess I would say.
All right. And anyone else would like to ask a question?
Sorry, before I leave problem-based learning, I want to say, I want to say one more comment about this. There's one thing that it's very hard once you become an expert in any subject. It's very hard for people to not believe that people really have to learn all this material about the subject before they can really be given problems to solve in it. And there's some really quite spectacular demonstrations of how that's wrong, where there's some experiments done where they had the students do in the traditional way of gave them all this information and so on, and then had them solve work practice using that to solve problems. So very much like we do in usual teaching. And the comparison though was to give them the problem first. So they couldn't solve it. They didn't know how, they didn't know enough, but the problem was such they could start thinking about what was necessary to solve it and how, trying to think about solving it, how you would possibly go about it. And then they were given the information they needed to solve the problem. And so these two groups of problem first, information to solve second, versus information first, problem practice second. And then they gave them a new problem. And it was about a factor of 10 difference in how good the students were who'd had the problem first in sort of learning the problem solving method. So it's,
essentially you're saying that students learn better if they think that they are solving the thing on their own without prior knowledge.
I'm not saying I'm not saying they're thinking they're solving it on their own. They're trying to solve it on their own.
They're trying to. Okay. All right. Okay.
And so and you can understand why if you look more detailed about how the brain organizes information. That if they're trying to solve this problem, and they know they need to know certain information, then when you give them that information, it's organized in the brain around solving this kind of solving this kind of problem and what it's useful for, as opposed to if you give them the information first, they just memorize it as isolated little pieces of information, and then they don't have the capacity to apply it when it's needed. And so it's kind of like lives off in this part of the brain as opposed to over in the problem solving part of the brain. And
there is a question from Miss Roslina Wati. Marco, yes.
Thanks very much, and thank you for the great talk, Professor Wieman. That was fascinating. My name is Marco Angelini. I manage outreach programs into schools from the University of Technology, where we've based all our practice on a design thinking pedagogy, which has some similarities to PBL. But I wondered if you could just say a little bit more about what you think the utility of design thinking approaches is to student learning, and in particular for younger students. I mean, we deal with a lot of high school age students, and it's all about getting them to think more practically about STEM, but engineering in particular. We get students to design prototypes through kind of tinkering approaches, very, very hands-on group-based approaches, where they're developing their own prototypes to solutions which they select themselves through that design thinking process. We're getting good results, and it seems to be engaging for the students, but I just wondered if you knew a little bit more about that, and just your thoughts on that whole approach.
So in general, the general approach is really at some fundamental level very much the same, because in design, I mean, the contrast to design thinking was, well, students are never making any decisions. There's no room for kind of creativity or individual thinking. It's because they're being given problems where they're all following set procedures. There's only sort of one solution and one approach to that solution. And so design thinking was intended to try and find, okay, let's give them something that there's some thinking involved as opposed to memorizing procedures. So So what I would argue is that to that extent, there's a great deal of overlap between what I'm talking about and the design thinking. What we've done is really it's a bit more detailed, systematic way to think about what is the thinking that you need people to do. Because in some aspect of design thinking, they're going off and building something or making some prototype, but that's awfully specialized, and they really, and so what I'd say is you have to kind of go beyond the general design thinking prototype and say, what is the specific kind of decisions you want them to learn to make in what kind of context? And then you go through if you like, the design process. It's really a problem solving process, but you need to think about exactly what you're having them to do, what content they're thinking about, because of not just getting them engaged and doing something. Those are important, but you want to make sure they're engaged in learning about the right kinds of things, the right later skills. And so I've just seen a lot of variation in the way people implement design thinking. So, you can have things kids are really excited about, but they aren't really, the things they're learning and excited about really don't transfer very broadly to a broader education. Whereas if you do the right kind of problems, or broken down into the right kind of decisions, you can kind of have a more generally effective.
So it's about being specific about how you frame the problems.
Yeah, and what you're thinking about having them do. But in both cases, to the extent you're always way ahead when you have them actually making decisions and making like realistic problem solving decisions that get so removed from the traditional teaching, unfortunately. So
yeah, making the real world problems does seem to help. Thank you. That was really interesting.
Yeah, okay, Marco? All right, okay. Prof, there is a question from Ms. Roslina Wati. Dear Prof, in what way does feedback inform students of their learning? In your opinion, what sort of feedback should be given to these students to maximize their learning? Can you give examples of effective feedback given to students to inform about their learning?
Yeah, so this is a very good question, and it's been quite carefully studied, actually. And again, I'll sort of start with, okay, what feedback do we give that's bad? What are some bad ways in teaching? And traditional teaching, students, can get very little feedback. That they'll be learning a bunch of stuff, then they have to take examinations, and some long, period after they take the examination, they get a score on it, and they say how well they did. That's really not very useful at all, because what we see about feedback that really enhances learning, it has three basic components to it. It has to be timely, and by that I mean it's changing people's thinking, and so it has to be given soon enough that they still remember how they were, they're working on some problem or something, they still know how they were thinking about it when they get the feedback. So it's timely, it's specific. It's not just, okay, you did this right or you did it wrong. It's, you did this part you did correctly, this part you did wrong because you forgot about conservation of energy. And then it's got to be actionable of, okay, so, leading them to what would you do to avoid making this mistake in future problems, and how would you identify in a future problem you might encounter that conservation of energy was going to be important for solving that problem. And then, so they have to have this timely, specific, and actionable, and then they have to have the opportunity to act on it. So they then have to go and practice another problem that allows them to put into practice the different thinking that they had before.
Okay, Leong Chan Craig from Singapore.
Hi, Carl. Thanks a lot for the wonderful talk. I'm just wondering whether you could give some basic insights on how you switch from a successful career in co-Adams to education. What makes you decide to do that? That's one question.
Well, sensitive.
No, I think Carl will be able to provide some insights into that. And on a more serious note, I also would like to have your comment on online courses.
Yeah, okay. So the first one is how I end up doing this. Well, I mean, for me, the first thing to realize is it wasn't an either or. I mean, I was working in atomic physics, doing research, trying to understand how I could help my graduate students learn to be better physicists so they could make me be more famous by, making great discoveries in my lab. And so that's what I started thinking about, is why they were struggling. And so for roughly 20 years, I was doing both kinds of research. And I did, a little over 10 years ago then, I stopped doing atomic physics research. And, that was, 10 years or so after the Nobel Prize. And to focus on just the education part. But that was really because I wanted to launch this big experiment at University of British Columbia on trying to see if it was possible to change how essentially an entire university taught science, and sort of as a big experiment in institutional change. And I made the decision really because I thought at that point that was just a really important step that nobody else was in a position to do. And it was kind of, in many respects, equally intellectually challenging, but the implications were just a lot broader than anything I was further going to be able to do in atomic physics. So that's that question. The question about online or virtual learning, that's a very good question. And of course, it's one that lots of people are worrying about. But it is an important one because these kinds of the traditional teaching when done online is worse than in person. These, let's call it research-based teaching, like I'm talking about, we find transfers over quite well to the online environment. And so the difference is becoming even greater. And, and I can just go into a little more detail why, is that in traditional teaching, if you're just giving a lecture and so students are just watching a recorded lecture, that's much less kind of human interaction. There's it's much harder to pay attention to. There's many more distractions on the computer screen, et cetera. So the standard lecture is online is worse than in person, a lot worse. Whereas in the kind of teaching we're talking about, where students are actually having to solve, they're being given problems to solve, and they're working in small groups. We run those as Zoom breakout sessions, and the students actually, when 3 of them or 4 of them are together in a Zoom breakout session, they can interact there better than they can in a, when you're trying to divide 200 students up in a big lecture theater. So you can have them interacting with each other more effectively. You can, as an instructor, you can drop in on all those different Zoom breakout sessions. In a big class, I can do that much better on Zoom than I can in an individual class. So sort of seeing how monitoring how the different groups are doing. And of course, since you're having students, they're there to be working through some difficult problem and provide a solution. So that gets them fully engaged. There's sort of no alternative to get distracted because you have a very clearly defined task. And so that's sort of why this research-based teaching carries over much more effectively there's some issues in communication and certainly the technology problems that can come up that are not trivial. But other than those, the effectiveness of the teaching doesn't suffer very much at all. Whereas the trying to take over traditional teaching to online, you're starting bad and getting worse.
Right, thank you. Actually, on that note, I was thinking that nowadays we could learn quite well from cooking lessons on YouTube. And I was wondering if there are studies to look at how effective it is to learn experimental physics, for example, after all you're experimentalists, on online courses.
So I don't think there's any good data yet that I've seen. I know people are working on this, but I don't think I haven't seen good published studies yet on trying to do experiments sort of online. What we do have data is at the introduction to me, they were talking about this PhET interactive simulations where students can go in and basically, change the charge on an electron and see how the atom level changes and really see the scientific models and essentially do experiments there, but they're kind of optimized over the real world in terms of what you can change, what you see, and so on. And so that's not exactly the same, or it covers sometimes of goals of experimental physics of trying to understand the phenomena. And we do have good data showing those are more effective than actually real world experiments because the computer allows you to have better things seen and displayed and manipulated. In terms of other aspects of, getting real uncertainties and dealing with the uncertainties of the real world, those aren't going to be as likely as effective there. But I don't think there's any good. I haven't seen any good things or research really showing how to do that well at this point. But people are working on it.
Thank you.
On that note, on a similar note, quick, just a minute, if you want to. Carl, how is your PhET initiative with the online learning compared to the YouTube cooking class?
So I think you would say that the cooking class is a very different learning model. I mean, cooking really is about following procedures, right? I mean, there may be some level that you want to be some great chef inventing new dishes, but that's not, you don't learn that from YouTube cooking class. You learn to follow procedures, and YouTube helps you see what those procedures are. It's easier to see that than reading a cookbook, but it doesn't give you, doesn't give you this kind of deeper understanding of the subject that would allow you to predict, that how you could make a completely different kind of bread that, was wonderful. You don't get that whereas that is what we want people to learn from science, right? To solve some completely novel problem. And so for that, one has to develop these mental conceptual models of the phenomena, what all the variables are that matter, that go into determining the behavior of, you know, an atom or electrons and whatever. And so from, you know, from a YouTube video, that would again just be a lecture just telling you information. Whereas what the PhET simulations allow people to do is they allow people to, you know, the learners to change the variables and we have within the computer this complex model that essentially captures what's in the scientist's brain about these phenomena and the interrelationship of all the various factors that one can basically play with and discover those. And so it's operating at a very different cognitive level than what you get from a cookbook or a cooking show that you're watching. Is there a question from?
Yeah, there's Miss Roslina Wati there again. Let's go ahead.
Thank you. Yeah, thank you, Professor Wieman. I'm Rosalind. I'm from Brunei, from Universiti Brunei Darussalam. I'm teaching the primary science teachers science, yeah. So how to teach science in primary school. So I'm just curious about these PhET simulations. How is it suitable? How is it suitable to be used by the primary school students? I'm talking about upper primary school students, because they also learn components of physics in the primary level or elementary level.
Yeah. So one of the things that's just been an interesting and surprising discovery is that these PhET simulations are effective over a much broader range of student preparation. And it's really because to a large extent, the students making the choices about what they're changing and what they're watching and paying attention to. And one can also set the level of complexity for the different simulations. So, but I mean, most of these were developed really for the introductory, sort of university introductory science level. We found that they're used a great deal in secondary schools. They seem to work very effectively there. Many, but not all, are used in the middle school grades. Most of them are really too complicated for the primary school levels. PhET's always building. I mean, I'm just an advisor now. You know, the project is sort of separate, but they're always building new ones and to do new things. So they do have now a few that are covering mathematics, and a few that cover chemistry at at a level that's appropriate for primary school students. And I think there's probably a few from the physics ones, but it's, you know, most of them I would argue are too advanced, but you'd really have to look for yourself and decide. But I do know there are some that work well at that level. But like I say, I mean, going from, let's say, a 12-year-old to a 20-year-old is an impressive range to start with. Getting down to 6 or 7 is awfully hard. But I do think they're likely highly effective for the primary school teachers, where we know their depth of understanding, and particularly kind of their having the appropriate mental models of the phenomena is a big struggle with primary school teachers. And I do know that the PhET simulations have been used quite extensively and quite effectively for educating those teachers.
Okay. Thank you so much, Professor.
All right. Thanks, Ms. Rosalind. Prof. Ali, would you like to say something? Ask a question?
Yes. Prof. Wieman, that was definitely a very interesting talk. Just wondering, your research, the data collected was across a variety of students. I mean, it's not just good students become better. It will work for average to be good, and the age group, do they differ? I mean, is it the case of the younger ones who learn better, or that is my first question. And then my second question is, can you mold an average student to be equally good in theory and practical?
So I missed just the sound quality I'm having trouble with of you. The last part of that question, the last sentence.
Yeah, can you actually mold an average student to be equally good in theory and practical?
So that, so I can answer that question quickly. I don't know. I mean, we know how to teach more effectively both theoretical aspects and the practical laboratory aspects. Again, in terms of having them really practice the decisions they need to make in the appropriate context they do. So that's going to be effective at both, but my guess is, but beyond that, the research about how good you can have a student to be in both at the same time, I don't know, but my speculation would be that, it's a pretty informed speculation, that there's so much research that shows that it takes the brain just keeps developing through, and the more of this kind of intense practice it does at more and more challenging problems, the better it gets at those kinds of things. And so now if you're going to split the learners, essentially their mental exercise, if you like, between the thinking about theory problems versus thinking about practical problems, that's probably not going to be as effective as if they specialize. But that gets to be a very subtle question, because there's certainly certain areas of experimental physics where if you know a bunch of theory, you're able to do that much better, and vice versa. So it gets a lot of intermingling, and so I think it's probably not so easy to answer.
I think in that sense, the word theory here has to be distinguished between fundamental theory and more advanced research type theory.
Yeah.
Okay. All right.
But in any case, I think the general point is just, there's no good answer to that I can give. You do raise another point though that I think is important. And you, at the beginning, you were sort of talking about there's different variations in the students, and this is something that my group has been studying a lot recently, and we've been looking at Stanford students, because Stanford's a very elite university. Probably, I think it's the most selective in the United States. And yet we see in the introductory physics courses and introductory chemistry courses, there's a lot of students that are not successful, who do poorly in those courses. And so, for me, that was sort of a challenge, because by a whole bunch of standards, these are exceptional people, and yet they're not able to be successful, and trying to understand what's happening there. And what we're finding is happening is really that, and in many ways, it makes sense. When I talk about, okay, this person has to be practicing, thinking and practicing and learning, but it's got to be the right level of challenge. If you have, I'll just use the exercise analogy. If you want to make yourself stronger, you don't lift this as a weight up and down to try and do it. You also don't try and lift a house because you just can't make any progress. And so in the same way, to strengthen a muscle, it's got to be difficult but doable. And similarly, the practice tasks that these students have to do have to be challenging but doable. But so when we look at these students who come into Stanford, they're good in many different things, but there's quite a lot of difference in their detailed high school physics background. And so they go into a course and right now, and I don't think Stanford's unusual, I think it's typical that you have a substantial range of incoming preparation, and the course is giving challenges which for the very top students is not much of a challenge. They've seen all the material before. For the ones at the bottom, it's just way, they're 2 years behind, and you just can't expect people to catch up that rapidly. And so, all these things I was talking about, there is this issue that you do have to make a reasonable level challenge for all the learners to be successful. And we were able to take these students who were doing very poorly in the standard course and find out, okay, they had very weak preparation. And then we had something that gave them sort of the course that targeted their level. And we showed that, yes, then they could learn well. But that's just part of what you have to take into account in the optimization of the learning effectiveness, that the same kind of problems, the same kind of practice doesn't work for all students unless they're coming in with very similar backgrounds.
Yeah, thank you.
Thanks, Carl. Carl, on that note, on the same topic, can I say that, I'd not say, can I presume that almost all university entrances are about the same? You have to have a basic passing level in some A level, O level, and all this stuff, and then you get accepted into university. So when you say these entry students, the first year students have a 2-year gap, where does that come from?
So in the US, actually across the world, university entrances are handled in very different ways. And so in your country, I'm guessing in your country, I know most Eastern countries, there's a very strict set of exams, and how you do on those exams determine whether you can go to the university or not. In the United States, that's not the case. That they look at a whole variety of different things. You have there's letters of reference letters that teachers or co-work, people who supervise them and working or something, write, and then there's a big variety of other things that they have, and so that's why we can have such a difference in, there's certain subjects, basically math and writing is pretty similar across them, but once you get into anything more specific like chemistry, physics, there's the measures by which they're admitted are very different, and the high school, the learning school experiences of those students are very different as well. But since you raise this point, I'll make the rather controversial, but I'm quite certain it's true, that your way of admitting students is completely flawed. That these O-level exams, or what they're testing, they are testing nothing meaningful in terms of the ultimate capacity of those students to be good scientists, for example. The cognitive, if you like, the cognitive processes that you need to do well on those kind of exams is fundamentally different from what you need to be a good scientist. And most of those cognitive processes are developed at the university. And so you know, the idea that you can predict them early on from those exams, that there's a bunch of research on that, and it just says it's just not correct. You know, that of course, if you only let people into the university who do well on those exams, then you say, well, you know, all university graduates do well on the exams, but that's mixing up cause and effect here. So, and I think this is really important if you kind of start to think about the future of society, the future of workforce, where it's really you're wasting an enormous amount of human capital if you're using some artificial exam to filter out, you know, who can pursue which kind of career. You likely are missing many extreme people who could be extremely capable and contribute to society, and not giving them that opportunity.
Yes, that was nice. Yes, I probably on a personal level, I'll agree that on a humanitarian level, on a human rights level, yes, what we're doing is a bit off, flawed.
Yeah.
Yeah. Okay. Any other questions from anyone? Nobody? Prof. Ali, are you still around? Yes. Okay. Prof.
Yes,
Ali is here. Carl is here. So I would like to throw a wrench to the both of you. Some years ago, our university used to do what is known as a hands-on approach. So we would give a set of lectures, and we follow up those lectures. We bolster those lectures with a set of experiments. You can say it's expensive. You can say it's time-consuming, but I don't know. We saw some mixed results. What are your comments on that, Prof. Ali?
Thanks, Prof. Where we did that, what 20 years ago?
Yep.
Right. Until we have problem with accreditation.
Accreditation is a problem, yeah. But other besides
yes,
accreditation, yeah.
Yeah. For your information, we were doing pure engineering in the beginning, and then, but the thought at that time was we'd like to introduce a bit more practical in the curriculum. I guess we went a bit overboard probably, and our board of engineers reckon that it was, you know, it's more of engineering technology rather than engineering. And but again, having said that, we are still very much practical oriented, and I think the idea is workable, and that's the very reason why I was asking you earlier on whether it's actually possible to train a person to be equally good theoretically and practically. And those are the kind of engineers that the industry requires, not just here, everywhere for that matter. So coming back to your Prof, I think the comment is said, I think was we are into the end of the second decade of trying to do it, and we're still improving on how to do it. And now that we have engineering technology in our midst, I mean that the idea, Prof, is not to make engineering technology as a second tier program, but to be equally good as the pure engineering. But it's just it's there to offer different choice to the different bunch of students. So, Prof, I mean that's a comment for now.
So when you asked me the question before, I was thinking in terms of physics, and I would have given a different answer when I think about engineering, because you know, physics can have problems and solutions that are completely theoretical, completely abstract, and you know, and then it has other things that are quite experimental. I don't think engineering has any, no good engineer does something completely abstract and impractical. Engineering is about solving real problems in the real
Ouch.
world. And so I think, that there's a lot, so every engineer I know who's good necessarily brings theoretical and practical strengths and capabilities to solving problems. And so at least I've never, in all the ones I've interacted, not nearly the same division as in physics. And so I think, yeah, there wouldn't be nearly as much separation. But back to the question about having students do practicals or, instructional labs. I have to be careful here because these take such different forms at different institutions. But my group, and led by Natasha Holmes, who's now a professor at Cornell and still is advancing this field a lot, did some very systematic studies about instructional laboratory courses in physics and how well students actually learned the physics underlying, that the experiments were involved in. And we found it was astonishingly low. We actually worked out some ways to measure this that turned out we could do with lots of students and very clear, clean comparisons. And we just showed that having a student go through these laboratory experiments was not having any impact on their learning compared to not having. And we actually then collaborated with a number of other institutions who used our technique for measuring this, and they were seeing the same thing. And ultimately, it was easy to, or not easy to understand, but it was clear the reasons for this, which is that all of these these instructional laboratories of the type we were having, have students go through and essentially reproduce the experiments that demonstrate, conservation of momentum or something, or, various electricity things. But to actually conduct those experiments, you don't need to know anything about the actual physics behind it. Now, to design a good experiment, to do this, you have to understand a lot about the physics. And you have to look at the results and see what they tell you. But all of that thinking, that cognitive processing that goes into actually doing the science discovery, that's removed in what students actually have, the thinking students actually have to do in those contexts. And so we and mostly now Natasha has really been doing a lot of work on thinking about what are the unique kind of cognitive processes that you can learn from an instructional lab, and how do you build that into the instructional lab. And not surprising based on everything I've said, it turns out there's a whole bunch of things where the normal instructional lab gives the students the things to do, whereas a good learning experience gives students the decisions they have to make. And so, posing, okay, here's what you want to, you need to accomplish. You're going to do that. You have to decide, how this experiment should be set up, or what data you should have to get, or how you should have to analyze to test what's happening. And so these experiments, the instructional labs in which the students aren't told what to do, they're just told what decisions they have to make, those turn out to be much, much more effective learning experiences. And that carries over where you have, I'll call them project labs, where people actually have to decide on their own project and design and carry out something. And so that they're now having to go through the cognitive steps that a scientist or an engineer would do. Those then are much more useful. But from a just a logistics practical point of view, those are difficult to run. They are expensive and so on. So, but the traditional ones as done in the US, our data shows they're just complete waste of money and time. So if I don't see any other hands up, it's getting a little late here for me. So you don't mind?
Sorry, I think we can call it a day off here then. One last question from our organizer here, Mr. Dr. Nazri. What is your opinion on the culture of education, Asian versus Western, in terms of this new approach of teaching science and engineering?
It's very hard to comment on that just because unlike science, which is and engineering, which are very similar, all over the world, the education is different and it's organized differently, it's funded differently, it has, different principles and structures. And so it's just very hard to make, all I can say is, yes, there are substantial differences. Now, what's good and bad about it, that's too complicated to answer, really. So.
Okay. Yeah. Sorry. Yeah. I think we're done with that then. So we will cut our session, our colloquium here. And thank you very much, Prof, for the most illuminating talk, and also the lively participations from others, Prof Ali included. We would like to move on to the photo session, but before that, I would like, on behalf of the organizers, I would like to apologize. We are very sorry for the technical problems earlier that we had on the videos as well as the audio. And now, before we say goodnight to Prof. Carl, I would urge everyone to turn on your cameras and say cheese. Tanika? Okay, just a minute.
Nice to see all of you now.
Yeah. All goes earlier. Okay. Cameras, people, cameras. Prof. Raymond. Okay, we are done.
Okay.
All right, okay, thank you, Carl, for your time and for your for delivering a most pivotal idea in STEM education. We hope you'll be able to guide us further down this path, and we wish you a good night.
Okay, thank you.
Thank you. Good night. Okay. Night. All right. Bye. For the others, dear ladies and gentlemen, the attendance QR code will now be given. Mr. Shah, the QR code, please. UniMAP students, please scan the code on the left-hand side only. And all other participants, including UniMAP staff, please scan the code on the right. And with that, we have now reached the end. We thank all participants for attending this Series 2 colloquium, and we hope that you're able to attend the Series 3 in January 2022. Happy New Year. Thank you and have a good day.
Tidak. Untuk scan QR code.